Now we're going to write our very first vertex and fragment shaders. So this will be our first full-fledged OpenGL application. Open up the Lesson 1.3 project and take a look at the program.cpp file, and notice that it's the same program.cpp file that we used in the last lesson. This will be the pattern that we use going forward. The renderingGame.h file has extended a bit. Instead of just overriding the draw method, now we're overriding an initialize and a shutdown method as well, and we're supplying the notion of a keyboard handler. We'll explain that here in just a minute. We've also got a couple of additional class members, and the one that we'll focus on in this demo is the pointDemo class. That pointDemo class is going to be a game component, specifically a drawable game component, that contains all of the necessary information for rendering a single point onto the screen. If you look at the renderingGame.cpp file, the first thing in the initialize method is the mCamera object, and it's a first-person camera object that comes from the library. Now, we're not going to spend a whole lot of time talking about this because, frankly, we're not even using it in this demo, but all of the demo applications that we've written here are going to require a camera, even the pointDemo, which really doesn't use one. So just add it and skip it, and we're going to come back to it. The next thing to notice is the keyboard handler syntax. So recall from our last lesson that we had this add keyboard handler command, where we're going to populate our keyboard handler with an stdbind call to the renderingGameOnKey method. And if you're unfamiliar with the stdbind syntax, this allows us to take a non-static function and associate it with a function pointer. So we're going to take this mKeyboard handler and pass it into our add keyboard handler, and what it's really going to be is the onKey method. So the onKey method here is responding to the key press escape key. Right, so whenever the GLFW press action is set and the key that is being passed in onKey is the escape key, then we're going to call an exit function, and the exit function comes from the game class, and sure enough, this exit function calls GLFW set window should close. That's how we're going to specify all of our keyboard handlers going forward. So this is a very common pattern that you'll see throughout the lessons. The next call is to create our pointDemo component and add it to the list of components in the game class. And finally, we'll invoke the GameInitialize method, which, if you recall, iterates through all of the components and calls their respective initialize methods. The shutdown call deletes the heap allocated pointDemo class, removes the keyboard handler that we added, and then deletes the camera class that we had instantiated as well, and invokes the final game shutdown class. The draw method looks just as it did before. It hasn't modified at all. Clear the background to the cornflower blue color. We call game draw, and then we swap the buffers with GLFW swap buffers. So now how does this magic happen? How does this actually invoke the pointDemo? Well, recall that this pointDemo class is a component, and specifically that pointDemo class, drawable game component, and the underlying game draw method iterates through all of our game components and calls their respective draw methods. So let's look at the pointDemo class. So our pointDemo is a drawable game component, and it has this GL unsigned integer for a shader program and another GL unsigned integer for a vertex array object. And let me just point them out here, and then we're going to look at the implementation of pointDemo.cpp and see how they're used. Notice also that we're overriding initialize and draw from our drawable game components. These are the things that are actually going to be called whenever the drawable game component's draw method gets invoked or the initialize method gets invoked by the underlying game class. Let's look at the implementation then of our pointDemo class. Our pointDemo class, specifically the initialize method, that's where we're going to start. We're going to set the current directory. The set current directory is a Win32 API call, and we're going to set it to the executable directory. And our executable directory is where the exe file for this lesson13.exe is going to be, and all of our content is going to be relative to that directory. The first thing that we're going to do is load and compile a vertex shader. This is our first look at vertex and fragment shaders. And the important thing for you to take away from this is that vertex and fragment shaders are required for pretty much any rendering that you're going to do inside of OpenGL 4.4. If we look at the pointDemo vertex shader, it's very, very simple looking. It specifies this tag #version 440 core. And what that indicates is that we're using the 4.4 specification of GLSL, the OpenGL shader language, and the core profile. The core profile is something that was introduced in modern OpenGL that separates it from the compatibility profile. The compatibility profile goes all the way back to OpenGL 1.0 back in the early 90s. And the core profile then specifies just the newest functionality in OpenGL 4.4. GLSL syntax looks like this. We have a main method, and that main method looks just like a C or C++ main method, and it indicates the entry point of the shader. This is a shader. Specifically, this is a vertex shader, and this vertex shader operates on every single vertex that's being passed into the pipeline. Notice this special GL_position variable. This indicates the object position on the screen in screen space when it comes out of the vertex shader. We're going to specify this vec4. Remember that vec4 that we looked at in the very first program represented 4 floating point values? Well, here it is again, this time not as part of the GLM math library namespace, but because vec4 is an intrinsic data type inside of GLSL. This still specifies 4 floating point values, and we're specifying 0001 for every vertex that's coming through this shader. Now, that may seem a little strange, but we're actually going to process 1 point in this example. So specifically in 2 dimensions, 00 is going to refer to the very center of the screen. The pointDemo.cpp file is going to load that pointDemo vertex shader. I've got a utility class that's included inside of the library, the utility load binary file, passing in the pointDemo vertex shader, and coming out of that vertex shader is just an array of characters, just a dynamic vector for the vertex shader source code. What has to happen here is that OpenGL on the fly has to compile all of its shaders. The way that we do that is through a function call called glCreateShader. So the first thing that we're going to do is create a vertex shader itself. The vertex shader is just the name. This GL unsigned int is just the name that we're going to create with glCreateShader. And then we're going to specify all of the sources that go into that name with glShaderSource. So the glShaderSource call specifying the vertex shader name that we just specified, how many sources we're going to specify, just one in this case, and then a pointer to the shader source that we're associating with the vertex shader, and that shader's length. Next, the glCompileShader call compiles that shader. So if we had multiple shaders that were all part of the same vertex shader, they would all be compiled at the same time. We only have one shader source, and it's going to be compiled with the glCompileShader call. The next thing we're going to do, the very same steps, to load and compile a fragment shader. The fragment shader gets invoked for every fragment that might be output to the color buffer. Remember we talked about the back buffer, and specifically the color buffer. Well, a fragment shader is writing to that color buffer. Every single pixel that you see on the screen was processed through the fragment shader. So where vertex shaders operate on individual vertices, fragment shaders operate on potential pixels, on candidate pixels, and we're going to call them fragments. And we call them candidate pixels because they might be discarded. They might not actually make it to the color buffer. But if they do, then they become full-fledged pixels. In DirectX, this is called a pixel shader. So in OpenGL, this is known as a fragment shader. Let's take a look at our pointDemo fragment shader and see that, likewise, it specified that same directive, version 4.4.0 core, and it also has a main method. And this time that main method is initializing a color variable to a vec4 whose values are 1, 0, 0, 1. Now, that color variable is declared with the out keyword. Its data type is vec4, its name is color, and its keyword is out, specifying that this is coming out of the fragment shader. There was nothing coming out of the vertex shader explicitly, although implicitly we're using this glPosition variable to pass data between the vertex shader stage and the fragment shader stage. What the fragment shader is saying is that every color coming out of the fragment shader is going to be fixed with the value 1 in the red channel, 0 in the green channel, and 0 in the blue channel, and then 1 in the alpha channel. Our color buffer is 4 floating point values. Those values are between 0 and 1, 0 meaning black or no contribution for a particular channel, 1 meaning full contribution of that particular channel. If I wanted to have an entirely white pixel, this would be 1 for red, 1 for green, and 1 for blue. A black pixel would be 0, 0, 0 for the red, green, and blue channels. This specifies red as the 1.0 as red, 0 for the other two channels, and then a solid color for red. Coming back to our pointDemo.cpp file, we're loading and compiling that shader. Now, just as with your C++ projects, you need to link your shader programs after you've compiled them. And that's where this mShaderProgram member variable comes in. mShaderProgram's name is created with the glCreateProgram function. Similarly to GL's shader source, where we specify multiple sources to a shader, well, we specify multiple sources to the shader program with GL attach shader. So we're attaching to this shader a vertex shader and a fragment shader. And then we call GL link program to link those two together. And finally, we can clean up these temporary vertex shader and fragment shader objects because they're included in the shader program when we call GL link program. So we don't need them anymore and we can delete them. Finally, we call GL gen vertex arrays to create what's called a vertex array object. Now I'm going to spend a lot more time on vertex array objects here very shortly, but for now I want you to know that vertex array objects, they store state information associated with our shader programs. So we're going to dig really deep into that here very shortly. For now, I want you to know that we really can't render anything without them. So create a vertex array object with GL gen vertex arrays. The number 1 there specifies how many of the vertex array objects we're going to create. We're only going to create one. We have a GL unsigned int called m vertex array object. GL gen vertex array is actually expecting an array of vertices. We only want one, so we can just pass in the address of our vertex array object to get us a pointer to that. In the draw method, we're going to call GL bind vertex array to bind the vertex array object to the shader pipeline, and then call GL use program to specify the specific shaders that we're going to use. So the shader program that we had previously built, that's what we're going to use each time through this draw call. Next, we're going to call GL draw arrays with GL points 0 and 1. I've specified GL point size as 80 because if we don't specify the point size as a little bit bigger, we're only going to see a tiny little dot on the screen. So if you specify a point size of something bigger than 0 or bigger than 1, then you'll be able to see the point a little bit more clearly. GL draw arrays specifies the actual draw call. This tells the GPU to draw something. This says I'm going to send information from the CPU to the GPU. Specifically, I'm going to send points. Well, how many points? I want 1 point, and there's no offset that I'm going to begin with. I want you to start at the 0th point. We only have 1, so we're going to start at the 0th point, and we're going to enter exactly 1 point. GL bind vertex array 0 then unbinds the vertex array object when we're done with it. Again, I'm going to spend a lot more time on that in the future. Right now, I just want to get something rendering to the screen. So let's run our application and see what we've accomplished. All right, there's our great big red point. So now let's experiment with this application. Toggle over to your point demo fragment shader. And what we're going to do is make this a blue pixel now. So we're going to remove out the 1 for the red channel, 0 still for the green channel, 1 for the blue channel, and 1 still for the opacity for the alpha channel. And instead of 80 point size, let's specify 40 for our point size and run the application again. And there we have it. Now we have a little bit smaller of a point, and it's blue. If we specified 0 or didn't specify the GL point size at all, it might be really hard to see. Right there in the center of the screen is this little tiny blue pixel, and that's what we get when we don't specify a point size that's a little bit bigger. Now, we're typically not going to be just drawing points. We're really going to be drawing triangles, most often drawing triangles and lines, but points are one of the 3 primitive data types in OpenGL that we can work with. So there you have it. Congratulations. You have written your first full-fledged OpenGL application in vertex and fragment shaders.